Hello, everybody. I'm Fred Moyer, and welcome to my talk. I'm here to speak about monitoring Kubernetes-based container services with Istio. So I'm a monitoring nerd and developer evangelist at Circonus. I'm also an Istio geek. I created the first Istio community adapter for monitoring Istio-based services with Circonus. The Istio developers gave me that ship on a bottle, which is pretty cool, as a thank you for being the first person to implement a third-party adapter. I also like to dork out on observability and statistics. It's a lot of fun. So just a quick overview of what I'll be talking about. I'll first give an overview of Istio and why it's awesome. Then I'll do a brief refresher on service level objectives to set a baseline. We'll look at what a red dashboard is and how we can make it better with histogram-based telemetry. Then I'll do a brief walkthrough of the Istio metrics adapter I wrote and finish up with a couple examples of how we can ask the right questions of the services that we're monitoring. So let's start off with Istio. Istio is a service mesh for Kubernetes, which means that it takes care of all of the intercommunication and facilitation between services, kind of like network routing software does for TCP IP traffic. It can also interact with Docker and console-based services in addition to Kubernetes-based apps. It's similar to Linkerd, which is a service mesh that's been around for a while. Istio was developed as an open source project by teams at Google, IBM, Cisco, and also the Envoy team at Lyft. The project just turned 1 year old about a few weeks ago, and it's rapidly approaching version 1.0. Version 0.8 was released just last week, and Istio has found its way into a couple of production environments at scale. So how does Istio fit into the Kubernetes ecosystem? Kubernetes handles container orchestration, deployment, and scaling. Kubernetes is basically the data plane, the part of the infrastructure that carries the application traffic. Istio is the control plane, the part of the infrastructure that tells the application traffic where it can go. It handles policy enforcement, such as role-based access control, also known as RBAC, traffic management, such as rate limiting, load balancing, think sending 5% of the traffic to a new instance to test it out as a canary, and also telemetry syndication, such as metrics, logs, and tracing. Istio is kind of the crossing guard and reporting piece of the container-based infrastructure in Kubernetes. So let's take a quick look at the Istio service mesh architecture. Istio uses a C++ Envoy sidecar proxy for each of its microservices that it's servicing. Envoy proxies inbound requests to the Istio mixer via a gRPC call, and mixer applies rules for traffic management and syndicates request telemetry. Mixer is the brains of Istio. Operators can write YAML files that specify how Envoy should redirect traffic and what telemetry to push to monitoring and observability systems. Rules can be applied at runtime without needing to restart any of the components. Istio supports a number of adapters to send telemetry to Prometheus, Circonus, StatsD, SolarWinds, Datadog, and a number of others. You can also enable both Zipkin and Jaeger tracing, as well as generating service graphs to visualize the services involved. So way back around 7 or 8 months ago, when Istio was version 0.2, you had to install Istio under a Kubernetes cluster with a series of kubectl commands. But Google Cloud Platform has added this really cool, pretty simple one-click installer. Well, it's a couple checkboxes and then one click. So now you can essentially deploy an Istio-enabled Kubernetes cluster to the cloud with just specifying if you want Zipkin, Grafana. There's a whole bunch of options. And you can also deploy a sample application which shows you what Istio is capable of. You can get up and running very quickly, and then you can use Istio control or Istio cuddle, the command, to start having fun. So let's take a look at how we can do that. So Istio cuddle, I'm going to go with the cuddle pronunciation like Kelsey Hightower does for kubectl. It's used to manage Istio via applying YAML-based configuration files. And you can, when I run a command like this basically tells Istio, go ahead and parse this YAML file and then deploy the needed services to get something up and running. I'll show a couple examples of these YAML files in a few slides, but let's see what happens if we run this command against our Istio-enabled kube cluster. It gives us a sample application made up of about 4 microservices that essentially act as a test app for reading and rating book reviews. At the bottom of the screen, you can see that Istio provides us some metadata here, such as what version a particular service is at, how much traffic is going to it, how much traffic is weighted, and a couple other things that we can output for debugging. Here's an overview of the architecture of this example application. You'll see that each of these services has an Envoy sidecar attached to it to do routing. And this is kind of a nice setup because instead of listening to your developers complain about why one language is better than the other, you can take their tactics and make that part of your plan. Let folks use the language of choice and get rid of all your programming language wars. And so instead, you can listen to people argue about tabs versus spaces. This layout shows a product page service, a book details page service, 3 different versions of a review service, and a rating service. Istio allows you to abstract, say like the review service behind its interface so that you can send differing amounts of traffic to each, say if you want to do a blue-green deployment, or if you want to do a canary deployment of a risky new service and only send 5% of the traffic there. Another significant benefit of this architecture is that it allows us to gather telemetry from services without requiring that developers instrument their code. This has a multitude of benefits, from eliminating points of maintenance and failure in the code to providing vendor-agnostic interfaces, which reduce lock-in. And also, generally, I found when you ask developers to instrument code, and I've been greatly guilty of this in the past, it takes a long time, and even if it's simple, it just opens up stuff that you can avoid. So this is a sample YAML snippet from the file which constructed that sample application. So you can see here a couple of pragmas, the version in there, the name, and we also have an image specification which tells Istio what Docker image to pull down and get the container up and running to establish a service, and tells it what port to run on. So this type of approach makes it fairly easy to codify up a microservice-based application if you've got a set of Docker containers that compose it. And it is YAML, so if you miss a white space here and there, it can be a little bit painful, but overall, it's not too bad. So we can also apply YAML-based rules at runtime if we want to do something like a canary deployment. This snippet from a file tells Istio to send 80% of the traffic to version 2 and 20% to version 3. So that can be very useful. And you're essentially testing in production, but sometimes you need to do that for new services. Here's a look at what Kubernetes services are exposed by this sample application. We've got the details service, product page, ratings, and reviews. Note that the 3 different versions of the ratings service are hidden behind this abstraction. So let's take a look at the pods that compose this. So here are the different pods that Istio will deploy for this service. Oh, I'm sorry, it's the review service that has 3 different versions. We also have a pod for details and one for product page. So this is a fairly small microservices-based app. Istio also uses system pods to operate itself, and I've been told that this is kind of heavyweight, but to have this many pods. But if your application has any sort of complexity in more than half a dozen microservices, this quickly becomes inconsequential to the total footprint. So here, we've got pods deployed for Prometheus, Grafana, Istio Pilot, Istio Mixer, which is the brains, Ingress controller, which uses Envoy, assert authority, and an egress controller. So now that we've taken a look at what Istio is, let's do a quick overview of service level objectives to set the stage for how we should be measuring service health. So most folks here are probably familiar with the Google SRE book. The concept of SLAs has been around for at least a decade, but service level objectives and service level indicators are also becoming ubiquitous among SREs. The amount of online content around these terms has actually been increasing rapidly, and I've been struggling to keep up with it over the past few weeks to include some of the most recent content. 2 new books in early release, and they're coming out soon, are Seeking SRE. It has a chapter in there by Theo Schlossnagel, the CEO of Circonus, who's footing the bill for my trip here, and the Site Reliability Workbook, which has a great chapter on SLOs by some of the Google authors from the SRE book. So I'm going to pull in a few excerpts here from a YouTube video by Seth Vargo and Liz Jones that I recently watched, which I think explains this concept really well. I recommend watching this video to get an understanding. So the gist of that video is that SLIs drive SLOs, which inform SLAs. The service level indicator is basically a metric-derived measure of health for a service. For example, I could have an SLI that says my 95th percentile latency of my homepage requests over the last 5 minutes should be less than 300 milliseconds. A service level objective is basically how we take a service level indicator and extend the scope of it to quantify how we expect our service to perform over a strategic time interval. Drawing on the SLI example we talked about, we could say that we want to meet the criteria set by that SLI for 3 nines over a trailing year window. Service level agreements have been around for a long time. They're generally crafted by lawyers to limit the possibility of having to give customers money back for those times when a service didn't perform like we committed to. SLAs are similar to SLOs, but the commitment level is relaxed as we don't want our internal-facing targets to be more strict than our external-facing targets. We want to know when we hit our limits first internally before we hit something that we've committed to the customer. So we've gone over a brief overview of SLOs. Let's get to the fun part and talk about red dashboards. So over the past several years, there's been a number of emerging standards regarding combinations of indicators for quantifying both host-based and service-based health. Brendan Gregg introduced the use method a few years ago, which seeks to quantify the health of a system host based on utilization, saturation, and error metrics. For something like a CPU, we can use common utilization metrics for user, system, and idle percentages, and load average and run queue for saturation. The UNIX perf profiler is a good tool for measuring CPU error events, though we don't expect to see those often. The Google SRE book talks about using latency, traffic, errors, and saturation metrics as 4 golden signals. It's targeted at service health and is similar to the red method below, but it extends it with saturation. In practice, though, it can be difficult to quantify service saturation. So a couple of years ago, Tom Wilkie, works at Grafana now, introduced the red method. I talked to him about it in March at GrafanaCon, and he said it was just something he came up with and didn't really expect it to take off. But with the red method, we monitor the request rate, request errors, and the request duration. Service level indicators can be integrated as part of a red dashboard, and we'll see that in a bit. But wait, the title of this talk mentioned containers. Why aren't we looking at monitoring the containers? Containers are ephemeral, short-lived entities, and monitoring them directly to discern our service health presents a number of complex problems, such as the dreaded high cardinality issue. If you've got containers coming and going every few minutes, mapping metrics to those can give you a tremendous number of tags, which is going to make it difficult to scale with even some of the most high-performing monitoring systems. It's easier and more effective to monitor the service outputs from those containers in aggregate. We don't care if one container is misbehaving if the service is healthy. Chances are that our orchestration framework is going to go ahead and kill that container off anyway and replace it with a new one. So if we want to compose a red dashboard, let's take a look at what telemetry is provided by Istio. I've given a hint away here with the font color. Istio provides several metrics about the requests it receives, the latency to generate a response, and some connection level metadata. It also gives us the ability to add metrics tags, which are called dimensions in Istio, to the telemetry. So we can really break down the telemetry by host, cluster, et cetera. But like I mentioned before, what we really want to focus on is the health of the service as a whole. See a lot of cameras going up. I'll pause a second. So red dashboards. Istio provides us with the components that we need to construct one. We can get the rate component in requests by second by taking the first derivative of the request count. We can get the error rate by taking the derivative of the request count of unsuccessful requests. Istio provides us with the request count, but it also provides us with dimensions on that. So we can sort those counters by successful requests, anything that's a 2xx versus something that's a failure, like a 4xx or a 5xx. And Istio also gives us the request latency of each request so that we can record how long each service request took to complete. So these three key metrics give us the building blocks that we can construct a fairly complete view of the health of the service. So let's take a look at what dashboard we get with Istio out of the box. That did not turn out well. Let's see. Okay, this VGA adapter is biting me right now. But there's essentially a number of panels here which show different metrics. Let me skip to the next slide. That's a little bit better. So the dashboard that Istio provides us already contains a number of panels that satisfy components of a red dashboard. In the upper left, we've got request rate, successful requests per second. We've got error rate in the upper right-hand corner, and we've got request duration in the bottom corner, in the bottom. And let's zoom in and get a little bit closer in those. That's better. So here we can see the first component of a red dashboard, specifically number of requests per second. It's essentially any request that returned a 200 response code, and we can graph that over time, something most people are already collecting. We can do something similar with errors. We can count up the number of 400 or 500 responses in this case and plot those to get an error rate, which is the E component of the red dashboard. Now, Istio provides us those system tags. So here we can differentiate Istio system-related errors, which are generated by the Envoy sidecar proxy, from Istio application errors, which are generated by the default product page. And then there's duration. So here we're, the Istio default dashboard collects data via Prometheus. So it provides a set of percentiles, in this case, 50th percentile, 90th, 95th, and 99th percentile, and graphs them. And while these four percentiles give us some overall indication of how the service is performing, there's a number of deficiencies with this approach that are worth examining. For example, during times of very low activity, these percentiles can skew wildly because of limited number of samples, and that can lead one to misinterpret system performance in these situations. Let's take a look at a few other issues that can arise with this approach. So percentiles are generally better metrics than averages, as you're expressing a range of values with multiple data points instead of just one. But like an average, percentiles are an aggregated metric, and they're calculated over a fixed time window for a fixed data set. If we calculate a duration percentile for one cluster member, we can't take that and merge it with another cluster member's percentile to get an aggregate performance metric for that cluster. And the reason for that is that you cannot average percentiles. I'll say that again. You cannot average percentiles, except when the distribution that was used to generate that percentile for each case is essentially identical. But if you haven't recorded the distribution that you used to derive that percentile, you don't know that you can average them. So it's a bit of a chicken and egg problem. This also means that if you've got percentile, 90th percentile for pod A and 90th percentile for pod B, you can't use that to calculate 90th percentile for the service that's composed of pod A and pod B. You're only measuring percentiles there for individual cluster members. So while this percentile-based approach gives us some indication of performance, it limits our ability to set meaningful service level indicators and as a result, meaningful service level objectives due to only having 4 latency data points over fixed time windows. So when you're working with percentile-based duration metrics, you have to ask yourself, are my SLIs really good SLIs, or can I do better? Has anyone here seen this video? Am I showing my age? I watched this in grade school. It's a great Donald Duck animation of math. So I believe that we can do better than percentiles, and in this next part of the talk, I'm going to focus on how we can use math to generate the service level indicators to give us a comprehensive view of our service's health. So let's push on and have some math fun. And we'll start off with histogram-based telemetry. So this is a histogram. It's a visualization of latency data for a service in microseconds. The number of samples is on the y-axis, called the sample density, and the sample value, in this case, microsecond latency, is plotted on the x-axis. This is the open source histogram that we developed at Circonus called the log linear histogram. There are several other histogram implementations out there in the wild that are open source. Ted Dunning's T-Digest histogram is one, which uses centroids for creating approximate histograms. There's the HDR, high dynamic range histogram, which is excellent. There's cumulative histograms. I believe those are in use at Google's Monarch. The Envoy project recently implemented the C version of this log linear histogram to collect Envoy telemetry as distributions. And they actually, in doing so, they found a minor bug in our histogram library, but we were quite happy to fix that. That's the beauty of open source. The more eyes you have on the code, the better it gets over time. Histograms have a property of what's called mergeability. I can take this distribution and I can combine it with another distribution as long as the bin boundaries are identical. Mergeable metrics are really ideal for monitoring and observability as they allow us to combine outputs from similar sources such as service members and calculate aggregates to obtain aggregate service metrics. So here's another view of the log linear histogram. As you can see, between 100,000 microseconds and 1 million microseconds, we chop that up into 90 bins. You'll also hear the term bin be phrased as bucket. You know, potato, potato. Wikipedia says bin, so I've gone with that. And once we hit that factor of 10 at 1 million, we increase our bin size by a factor of 10. So what this allows us to do is have a fairly easy to implement histogram standard here that scales and gives us statistically meaningful values at higher values and also at lower ranges as well. The actual library here, I think, has a range of 0 to 128 exponents. So it captures an incredible range of values. In practice, the number of bins needed to represent a latency distribution like this, we found to be around 300. We don't tend to see operational workloads that need more than 300 bins to represent a distribution. So here you can see how we've overlaid a couple of aggregates onto this histogram. There's the median, which means that half of the values are below this value, or half of the samples are below this value, and half of the samples are above. The average is basically the sum of all the samples divided by the number of samples. And you can see how that's different here in this basically a single mode Poisson type distribution. A 90th percentile is over there at 1 million, and the 90th percentile is the point at which 90% of the samples are below that value. Now that doesn't tell you, what's to the right of that value. I could have other samples, way out there at 100 million, but I can still have 90% of my existing samples below that value. So we can bring up SLIs that we talked about earlier, and when we have latency data displayed in this format, we can pretty easily calculate our SLI for a service by taking histograms from different pods, merging them together to get a 5-minute view of the data. Say if we're collecting data in 1-minute distributions for each pod, because histograms are composable and mergeable, we can merge those together to get a 5-minute view and combine those from each of the different members that are composing our service. And with that, we can get an overall value and calculate the 90th percentile for that combined distribution. And if it's less than 1,000 milliseconds, we've met our SLI. Previously we showed the Grafana red dashboard graph with 4 percentiles, the 50th, the 90th, 95th, and the 99th. We can overlay these percentiles onto this distribution and kind of get a coarse guess as to what the request distribution might look like without each of the individual bins. But you can see that we would need some sort of quadratic equation, and we'd be making a lot of assumptions because distributions don't always look like this. What could it look like if the distribution had different individual modes? So this histogram shows the distribution with two distinct modes. The leftmost mode could represent fast responses due to requests being served from a cache, and the right mode could represent requests or responses being served from disk. Just measuring latency using 4 percentiles will make it nearly impossible to reconstruct a distribution like this. So this gives us kind of a sense of the complexity that percentiles can mask. But operational data, especially in complex microservice architectures, can do weird stuff. What if we had more than 2 modes? So here, just looking at it coarsely, we've got at least 4 visible modes. If we were to do the math on the full distribution, we can actually see that there's 20+ modes here. How many percentiles would you need to approximate a latency distribution like this? The answer is probably close to the number of bins in this distribution. But it can get worse. When you've got, like I said, when you've got a complex microservice architecture, it can exhibit modes that you're not going to be able to predict. But when you're capturing data as distributions, you can visualize it and see what your service is actually doing. This type of histogram visualization shows a request latency distribution over a fixed time window. But we can, say 5 minutes. But we can store multiple distributions to get a sense of how something like this request distribution changes over time. So this is a heat map. This was generated by the Grafana open source library. The data was stored in an IronDB time series database and fed into this visualization. So this represents the response latency from a cluster of about 10 Golang-based load balancers. This is about a week's worth of data, and there is approximately 1 million samples here. You can see that the median response time for the load balancer hovers around about 500 microseconds, and that's represented visually by the red band running through the center of this. If we were to see that red band shift up for increased latency, we would know that our service is slowing down and that something's gone wrong. This is a different type of heat map. This is the visualization we use by default in Circonus. You can see the distribution here also. The darker regions represent clustering of values. But what we've done here is, I talked about percentiles before. I'm not bashing percentiles. They're great, but the way to really use them well is as outputs, not inputs. Here, we can use this distribution to calculate how these percentiles change over time, and we can see, as the system becomes under more load, that 95th percentile rises up, and you end up seeing actually, how much, by how much you're exceeding your SLI over time. So this really gives us a good way of, showing the actual behavior of our system. And let's bring it back and create an improved red dashboard based on the graphs I've just shown you. So here we've got, request rate, upper left-hand corner, error rate, upper right-hand corner. We've got a distribution in the form of a histogram for this time window. And we've also got that broken down into a heat map for this time window to show how the individual distributions we've collected over time change. So with this layout of a red dashboard, we can get a fairly complete view of how our service is behaving with only a few panels of information. This particular dashboard, again, was implemented using Grafana. Latest Grafana has some really cool features, including this heat map. But we can extend this a little bit further too, and drop service level indicators on here. For the rate panel, our SLI might be, hey, we want to maintain a minimum level of requests per second. If it drops down to 0, something's probably wrong with our service. For the error rates, we want to keep the errors under a certain level. If we exceed that, we violated our SLI. And as we've looked at duration SLIs previously, we want our 99th percentile to stay under the red line, and we also want it to, individual buckets of that to stay under the red line too. So, we can, using Istio, we can grab telemetry, store it as distributions, and set SLIs that are really meaningful for us. We have a lot more to work with than just, taking aggregates and trying to set SLIs based on those. And as we'll see in a bit, we can use this type of data distribution to ask some complicated questions about our business. So let's move on and take a minute to see how we actually get this data out of Istio. So Istio provides developers with an adapter API that they can use to create their own custom adapters for telemetry syndication, as well as traffic management and policy enforcement. The Istio mixer is written in Golang, and it gives you a set of predefined handler endpoints that you can write a Golang package to receive request and response metadata, and you can act on it. The development team is currently looking at an option for out-of-process mixer adapters so that information would be exchanged using gRPC, but we'll be looking at the in-process implementation, as that's kind of currently the production, what's being used in production. So along with Go code, mixer developers also create a set of YAML files to tell the adapter what data to receive and what to do with it. So let's take a look at the code. I'll give folks a few seconds to bring up the code repo on Microsoft, on GitHub, if they want and follow along there. That was a little Microsoft joke. They bought GitHub, as everyone probably knows. So this is the root level of the adapter I wrote. We basically got a couple components here. Circonus.go is the actual adapter that implements the telemetry syndication. Circonus_test.go implements a number of unit tests to make sure that it's working okay. The config directory holds a YAML file that basically tells Istio how this particular adapter is, expects to receive information. And the operator config is essentially a sample configuration that I provided so that users can grab that and get up and going pretty easily. And there's actually been a lot of adapters made, even in just the past 6 months. The Circonus adapter I showed you, I got the PR merged on that, I think, December. And since then, there's been adapters developed for CloudWatch, Datadog, SolarWinds, Stackdriver, and I would expect more to be coming. So there's a number of different telemetry systems that you can push data to. And it was pretty fun to see more telemetry adapters get added after I finished the first adapter, because I wrote up a document and gave a report to the development team what was fun about it and what wasn't so fun. Initially, the project was using the Bazel build system to build the Istio mixer executable. And I attended a couple of meetings where there were some mixed opinions about its ease of use and value. And I was able to chime in with my experiences as an outside developer as well. Eventually, they dropped the Bazel build system and are going with just a pure Go build system. So this is the meat of the adapter. There's a handle metric function which takes a context object and a slice of metric instances. The handler object already contains an instantiation of a Circonus client library, which is the glue to our SaaS system, and that's open source. The logic here is fairly simple. We've got a for loop there, which operates on each of the metric instances, and it says, hey, what kind of metric is this? Is it a gauge? Is it a counter? Or is it a distribution? And then it takes that metric and it uses the telemetry client embedded within that handler object h.cm to basically record that value. So the amount of code it took to implement this in the end was actually very little. I don't know, maybe 20 lines or so, if that. H.cm uses that log linear histogram implementation under the hood that I showed earlier, so that when we record a distribution, it stores it as within a histogram structure in the telemetry client. And if all this looks pretty simple, that's because it's a good client that I was using, and most of the complexity is abstracted behind that. If you take a look at some of these other adapters, the Prometheus one is fairly complex since it has to start up an additional Prometheus scraper. The StatsD one is fairly simple. Some of the newer ones, the DogStatsD one is fairly simple. I haven't looked too much at SolarWinds, but as the APIs have gotten better over time, it's like I showed you here, it's fairly trivial to go and, well, not trivial, but it's not too difficult to go and write your own client to say if I want to take data and I want to push it to my Logstash. Or no, I'm sorry, my Elasticsearch cluster. And that's not too difficult to do. So I've highlighted, in red, the parts of this which are related to our red dashboard. So counter metrics are and distribution metrics are. Now that handler struct I mentioned before, it's got a few members here. It's got our telemetry client. It's got a reference to it, actually. And during this development, I found out the hard way that I needed to declare this by reference and not value. So enough said about that. It's got an environment element, which basically encapsulates some of the common Mixer functionalities, such as logging, an interface to a job scheduling daemon, and some other Mixer utilities. The third element is a metrics map, which contains the maps of all the metrics that we configured in the YAML file to tell Mixer what we're expecting. And it maps that to the list of what's being provided through the interface. Now, cancel, if there are any Golang programmers here, is a really cool structure. This basically contains a context cancel function, and it allows me to set up a context that is available to other callbacks. So it's almost like a teleport mechanism. When Istio shuts down, I can call m.cancel, and that will trigger a metrics flush in remote parts of the code, which basically takes care of flushing any additional metrics and any code cleanup destructors. So here is YAML I had to write, and all this does is basically tell Istio, hey, this request count metric that Istio provides, I want that to be a counter data type, because then I can go back here in my handler and do a case comparison on type and submit that metric appropriately based on what I'm expecting, what type of data structure I'm expecting it to be. I'm expecting request duration to be passed as a distribution, which is, it's a time.duration value. And I believe I cast that to a float 64. And I don't use request size and response size in the red dashboard, but I can pass those as gauges. So because Istio is designed to run at high QPS rates, we don't syndicate metrics for each request. We tell Istio to fire up a daemon in the background, which flushes the metrics client at regular intervals, and also flushes metrics when Istio shuts down. So writing an Istio adapter is fairly straightforward. If anyone's going to OSCON in Portland in July, I'm going to be giving a tutorial on it there. And also, I'm happy to walk through this code in depth with anyone after the talk if they're interested. So we've kind of taken a look at the pieces to get meaningful data from our services. With a red dashboard, the Istio metrics adapter, histogram-based telemetry, and service level objectives. So let's see what kind of questions the business asks, which we might be able to answer with this. So we all like to solve technical problems, but not everyone has this focus. The folks on the business side want to be able to answer questions on how the business is doing, because that's the primary reason for the business existing, even though the technical stuff is really fun. So let's take some of the tool sets that we've assembled over the past 50 slides and see what we can do with those. One question, oh, that picture didn't turn out well. One question you might be asked is, how many users got angry when things slowed down on Tuesday after marketing sent out a big email? Another question might be, is service A under-provisioned or over-provisioned on our purchasing checkout? And there's other business-centric questions folks will ask that we can use all this telemetry to answer. So slowdowns, everyone's dealt with these. Marketing sends out an email and end users say, hey, the site got really slow. How can we quantify the extent of how slow it was for everyone? How many users did we make angry? Marketing wants to know that so that they can send out another email blast with a 10% discount and to all the users, but hopefully not create the same type of slowdown in doing that. So let's try to figure out an SLI and assume that users get angry if requests took more than 500 milliseconds. There's a couple of well-documented resources out there on the web on how fast it takes humans to realize, when something's going slow. Humanbenchmark.com I grabbed. That says the median reaction time for humans about 215 milliseconds. So we're assuming that people start to, what I call rage click when things take more than 500 milliseconds. So how can we calculate how many users got angry with that 500 millisecond SLI? Well, first we record the latency, request latencies as distribution. And then we can plot them as a heat map, as we saw earlier. And we can take that distribution data and we can calculate what are called inverse percentiles. When we calculate a percentile, like what's my 99th percentile, it could say, oh, that's 300 milliseconds. But what that doesn't tell you is how many requests took longer than that 300 milliseconds. That's where inverse percentiles come in. With an inverse percentile, I can say, for 300 milliseconds, what percentage of my requests took longer than that? What's the damage? I know I violated my SLI, but how much did I violate it by? How much damage did I do? And we can take that percentage of how much damage we did, multiply that times the total number of requests in that time window, and we can integrate that over time. And that should tell us, how many people we made angry. So we can plot that as a line on this heat map. This is similar to the heat maps I showed earlier. Histograms are represented over time. This big outage here, where request latencies go way up, that I've circled, you can't see the y-axis because of the VGA resolution, but that corresponds to about 4 million requests that exceeded our SLI. So, we missed our SLI for 4 million requests. Whoops. One other thing that isn't quite as obvious are the additional outages on the right. There's two, slowdowns over there, which generate, 2 million requests missing their SLI each. So that's an equivalent amount of magnitude, but it's not nearly as obvious as this one. And another one that's kind of a false positive is that this part right here, that concentration, it looks like that should be a slowdown, But because we're using math to calculate, our SLI, and then, calculating an inverse percentile to see how badly we violated that SLI, it turns out that what looks like it might be a slowdown or a bad outage actually wasn't that bad. So what you see is not always as meaningful as what you can calculate. And we can do these types of mathematical analysis and answer these questions because we're storing data distributions, not aggregations. But bear in mind, again, the percentiles and the inverse percentiles are the outputs of those calculations and are always extremely important. So here's another common question. Boss comes to you and he says, is my service under or over provisioned? And the answer is often, it depends. You get load variance from, varies from time of day to day of the week, and in addition to special events. Not to mention, different types of user activity can affect how the system behaves under load. So, we can put some math to work again and use what are called latency bands to visualize, how our system is performing. So this is a graph of latency bands. And what this is essentially showing is the number of requests under 25 milliseconds, between 25 and 100 milliseconds, 100 to 250, 250 to 1,000, and above 1,000. And that's all on a color gradient. So green is fast, red is slow. Yellow and orange are in between. So, our system starts out, and appears to be under-provisioned because everything's finishing really quickly. But as you can see, it slows down over, 10, 15 minutes, and we start to get requests that run really slow. So in a 15-minute span, our system goes from, under-provisioned to over-provisioned. And we see that this happens twice. In the second occurrence, it's a more gradual loss of fast requests, but also, a little bit quicker onset of requests that take a lot longer. So what does this tell us about provisioning? It depends. If you see something like this, your Kubernetes setup might be a good candidate for auto-scaling. GCP just added that. And we can add this type of visualization additionally into our red dashboard as another duration component. It's excellent for communicating with business stakeholders, as it doesn't require a lot of technical knowledge investment for them to understand the impact that this has on the business. So, what conclusions can we come to? We should monitor services, not containers. Services are long-lived entities, containers are not. Your bosses don't care how your services or how your containers are performing. They care about how your services are performing. Record distributions, not aggregates, but generate aggregates from those distributions. Aggregates are very valuable sources of information. Istio gives you a lot of stuff for free. You don't have to instrument your code either. You don't need to go and build a high-quality application framework from scratch. Kubernetes and Istio have you covered. And use math to ask the right questions about what's important to your business. That's what this is all about, right? When we can make systems reliable by answering questions that the business values, we can achieve the goals of the organization. Thanks, folks. I saved my obligatory proud parent photo for the end. Happy to answer any questions.